I am Yogesh, and today in this episode we shall be moving from the three laws given by Newton to some of its applications, and we shall be discussing some of the very important concepts in the field of mechanics that we are studying right now. So, as what we can recollect from what we studied in the last lectures was that there is some motion of the bodies, and in order to understand the motion and how the bodies are moving, we had Newton's three laws. The first law was that the state of inertia is something that every body wants to have always. Rest means rest, uniform motion means uniform motion, no disturbance. Then we had that the rate of change of momentum is directly proportional to the force. Larger the change of momentum, larger is the force. And also we discussed that the action reaction pair, how it happens and why is it so that the third law is applicable everywhere. That is right from an analogy of say suppose you have a bug hitting your car. From everything around this universe, these three laws are applicable in each and every moment that you encounter in our day-to-day life. So right now we shall be moving from these three laws, and we will go into the depth of some of the laws that came from these three laws that govern the world around us. Now the first thing that I would like to discuss with you is the momentum. So from the second law, what we can say that there is some momentum. A body is moving with some time, and there is a momentum, there is a change of momentum, there is a force that is acting on the body or by this body to the other. But what exactly is the momentum? Means how does it come into play? What is the role of momentum in defining the motion of the bodies? And is there something related to momentum that states that momentum is like this only? So suppose if I am saying that an apple looks like red always and it's a bit sweet. So is there something like the momentum's field that is in the field of momentum? Is there something I can say that momentum is always like this? Well, actually, if we sum up the three laws and if we consider a situation, for example, if I get selected in army and I am given a task to have a practice shoot. So I have a gun, right? So when I am holding the gun like this, and once I pull out the trigger, tuck, so what will happen is that the bullet will come out of the nose, and I will get some sort of jerk with that bullet. That is, once the bullet went out, I felt a jerk, and so it will hit this area, and I will say, oh, I got hurt. That's why they always advise that you must keep that at this portion, exactly at this portion, not here or not after that, because you will have some feeling of hurt that, oh my god, it just stuck me here. Well, why is it that? It is because whenever there is a change in momentum, there is always some sort of action reaction pace happening there. For example, when I fire a bullet, the bullet goes out. So there must be some change in momentum of the bullet. That is, initially the bullet was at rest, it was in some state of inertia. Now when I pull the trigger, I am making the bullet to move rapidly or abruptly. So what will happen is that in that course of time, it is I think hardly a second, or say 2 seconds, but not greater than that. So within that particular seconds time, the bullet is going from the state of rest to the state of motion. So what is this all about? This is nothing but the rate of change of momentum. So the bullet went out, but I have a problem right now, and the problem is that since the bullet and the gun that I was having, they were one system, So the momentum went out. Then why did it hurt me here? Well, actually the reason is simple. The reason is like that, since these two bodies are there, they are in contact with each other. So when the one body moved out of it, or one part of it moved out of it, the bullet, the other part, that is the gun, it will recoil back, because it has to conserve something. And why it has to conserve something lies in the third law of motion. That is, for every action there is equal and opposite reaction, and that is instantaneous reaction. That is, the moment I fire a bullet, it goes out, I will get a recoil here. That's what's happening here. So by following the first law, I got the inertia got disturbed. I went into the second law. I said the bullet's momentum changed, so a greater force came into existence. In order to counterbalance that greater force, my gun recoiled back as per the third law of motion, and that's why I got hurt here. So if I just wind it up and I go back from the third law of motion to the rate of change of momentum, what I am seeing is that, yes, I am saying that the momentum is getting conserved. That is, no matter whatever happens, if a body is isolated and if there is some sudden change in the momentum, the total momentum of that body will remain conserved. And if that is the case, that like I am holding a gun here, and one of my friend who is in army, he is holding me so that I don't recoil back with a gun, or I don't move back like this with a gun, what will happen is that you won't find a change, and then you will say, no, this thing is wrong. You said that there will be some recoil because I fired a bullet, so I must get hurt or I must move back. Well, actually, if you had paid attention to my statement, the statement was that if the system is isolated, then only this law will hold. So the basic idea of this conservation of momentum is that, provided the system is isolated, no matter how many parts it has. For example, if I have got a cracker, if the cracker is burst, there may be some thousand of particles and they move out in random directions. So the momentum will be conserved always, no matter whatever happens, provided the cracker is isolated. So this is the conservation of momentum, which comes out from the soul or the basics of the three laws of motion. Now, after discussing the conservation of momentum, I am feeling a bit tired, so I don't want to get disturbed. I will simply like to sit like this. I don't want to get disturbed. But suppose you come and say, no, you tell me what we should discuss right now. Well, I will only say I will discuss about the equilibrium of the bodies. That is, my choice was to be in a state of rest, to even sleep. That was my inertia, and then you came out and disturbed it. So let us talk about the equilibrium of the bodies, that why a body is always in a state of equilibrium. Suppose if you hang some coin or a pebble from the ceiling of a wall into your room, and then you will simply try to oscillate it. You simply do some motion like this with that pebble and you leave it. After some time, it will do some to and fro oscillations, then it will come to a halt, and you will say that wait, there is always a gravity, so this pebble should fall. But then you will see upwards and say, oh, there is also a string there, so the string is trying to hold it like that. So how is it acting? Means there could be two things: either the force of gravitation is not acting at all, so that it is floating or it is at some sort in the mid-air, or the tension or the force that is being applied by that string is more than the force of gravitation. I think these two things are not correct. The better statement is that the force or the tension that is produced in the string due to that mass there, like that the pebble there or some coin there, is equal to the amount of force that the gravitation is acting. Means with the force the gravitation or the gravity or the earth is trying to pull it is exactly equal to the tension that is produced in the string, and so it will remain intact unless and until you disturb it. Like at the start I was really tired, I was trying to sleep, but you disturbed me. So that is probably because I was trying to sleep, that is my state of equilibrium. So provided no one tries to come and exert a force over a body, the body will always remain a state of equilibrium, because then due to all the three laws, all the forces over that body is neutralized. One more thing to think of it is that some people always say that since there is a state of inertia, and that's why the body is always at rest, so we can say that the body is in equilibrium. There might be some case in which the body is moving with uniform velocity or there is no acceleration. So what will happen is that the body while moving is always cancelling all the components of force that are acting over it. So it is in some sense, or sorry, not in some sense, in any sense, that body is in a state of equilibrium. So this is the the state of a body when no force acts over it, all the forces cancel it, give rise to a very beautiful state that is called equilibrium. Now you must be asking this question that okay, I'm fine with the conservation of momentum, and I'm also happy with the equilibrium that everybody is having, but can you combine these two? Well, I will say yes, and that should be the case always, because since these two things, that is the conservation of momentum and the equilibrium, has originated from the three laws of motion, so we can have a case where these two things are happening. So let us consider a case. I think we should go for a very nice case, that is you must have played cricket. Okay, so whenever you are playing cricket and the bowler is bowling, so the ball comes to you and you will hit the ball with a bat. So that smaller time that is there in which the ball came into contact with your bat, that is the nothing but the rate of change of momentum, because your ball has got some mass, it is moving with some velocity. In that time the momentum is changing, larger force is there, and then the ball is moving. So after some time the ball will come into a state of rest. At that time you will say dead ball, or the ball is not in a play. So at that time the ball is in a state of equilibrium, neither you are moving it nor you are exerting some force over it, it is all the same. So if I consider this case, and if I go on for sorting out some analogies, in your whole home you have got so many things to think over it, and then you will say no, the three laws are in my hands like this. You want the first law, here you go, the second law, here you go, the third law, here you go, everything lies on your fingertips. But I've got a very good assignment for you. I have a question. Suppose if I'm running on a straight track, I can run as much long as I want. But if you say, okay Yogesh, you do one thing, you try to run on a curved track, and you getting it, that circular track, and after running a few minutes I say, oh no, I'm a bit tired, and I will say, oh I'm so tired, it is really very hard. So why is that happening? Means the person is same, the distance is same, and the pace is also same. So why is all this happening, that when I am moving or when I am running on a straight track, I can run much better and I can cover the much more distance as compared to when I am going on for a jog or I am running on a curved track. This is the riddle that we will try to solve in our next episode, and then I will be waiting for your answers. Now, before summing up all the things that we have discussed, that the momentum is always conserved and there is always a state of equilibrium for the particles, that there is some sort of state of inertia, or they are moving with some uniform motion. I would like to pose a question to you. The case is really very simple. An athlete is running on a straight track. He is running with a same speed all the time, and once he is running, he can travel a much longer distance. But when that same athlete is running on a curved track or a circular track, the athlete will complain that see, I'm getting tired, and you will be really very astonished to find that the distance that the athlete has covered while running in that straight track, that has produced some, I think he got exhausted. But if you go for the case where he was running in a circular track, he traveled much lesser distance in the stipulated time and he was much more tired than the previous case. This is the riddle that you have to solve, and in the next episode we will try to crack this riddle to find out what are the common forces that are all around us, what are the common forces of this world of motion, what are the common forces that comes into existence when we do something with the things around us that matters the most to us. So in the next episode we shall be discussing some common forces in mechanics. Thank you.